On March 24, 2026, Google researchers Amir Zondier and Vahab Mirachni published a highly technical computer science paper detailing a new algorithm called TurboQuant. It was a routine academic release. Within hours, it triggered a multi-billion-dollar panic across the global hardware market. Before the end of the trading day, the companies manufacturing the physical hardware that powers modern artificial intelligence watched their valuations plummet in a synchronized sell-off. This chart shows the downward plunge of major memory stock tickers in a single 24-hour window. SK Hynix dropped 6%. Samsung fell nearly 5%, with hits mirroring them across Micron and Kioxia. To understand the impact of this drop, look at the preceding 12 months. These exact memory stocks had just finished a massive 300% rally, driven by severe global shortages in AI hardware. Across the tech community, the reaction was explosive. Developers immediately dubbed this Google's DeepSeek moment, while others compared it to Pied Piper, the fictional startup from Silicon Valley known for its mathematically impossible compression. Billions of dollars in real-world hardware value evaporated almost overnight, and it was driven entirely by the mathematical equations published in one singular document. To understand why a math paper could move the market, we have to look at the physical limitations of artificial intelligence. Running large language models requires massive amounts of computational hardware. Inside those hardware arrays, there is a specific bottleneck known as the key value cache. Think of the key value cache as a high-speed digital cheat sheet. When an AI processes a prompt, it uses this cache to store its past calculations under simple labels. This allows the model to retrieve information instantly, rather than having to recompute every single step. This diagram illustrates a data pipeline being overwhelmed by the key value cache. While this cheat sheet is necessary for speed, it bloats rapidly. As models ingest larger amounts of data, the cache consumes vast amounts of high-speed memory. Solving this specific memory bottleneck dictates how fast and how cheap an AI can operate in the real world. It is the central challenge for AI research labs. The paper published by Google claimed that their new TurboQuant algorithm completely cleared this key value cache bottleneck, and it did so with zero loss in model accuracy. TurboQuant reduced the required memory footprint to exactly 1/6 its original size. Quantized down to just 3 bits, a 4-bit model achieved an 8 times performance increase computing attention logics, the math the AI uses to decide what is important, compared to a 32-bit baseline. These performance metrics are what filtered out of the computer science labs and onto the financial trading desks. Investors saw a 6 times efficiency gain and drew a straight line. If artificial intelligence suddenly needed 6 times less memory to function, the massive demand for AI memory chips was effectively over. Almost immediately, industry analysts like Ray Wang and Ben Berenger pushed back against the market panic. Wall Street had missed a critical distinction in the research. TurboQuant targets inference, the process of actually running the model for users. It does not reduce the massive amounts of RAM required to train the model in the first place. The analysts pointed out a simple truth of computing. Making an AI more efficient doesn't destroy the demand for hardware. Clearing a major bottleneck simply allows engineers to build much larger, more powerful models. Because memory is a highly cyclical sector, and these stocks had already gained 300%, analyst Ben Berenger noted that investors were likely just looking for a reason to take profit. In this view, the crash was simply profit-taking by a market that had misunderstood an evolutionary update for a revolutionary threat. But the financial market's reaction is ultimately a distraction from the real computer science mystery hidden inside the Google paper. Traditional vector compression requires heavy memory overhead just to calculate and store the quantization constants. To achieve compression, you usually have to spend memory to manage that compression. Google's claim of zero overhead, lossless compression broke those standard rules. The stock market panic tells us very little about the algorithm itself. To understand why TurboQuant caught the industry off guard, we have to look past the ticker symbols and look at the specific mathematical trick that bypassed the standard memory trade-offs. Every time you ask a large language model to read a document or write code, it generates millions of internal calculations, and almost immediately it starts discarding them. The model doesn't throw this math away because it's useless. It throws it away because the physical machine running the model literally has nowhere left to put it. We tend to think of AI as a purely software phenomenon, but it is entirely bound by the physical reality of the servers running it. Inside these massive data centers, memory space is finite, and it is expensive. When an AI processes a long prompt, like reading an entire book, it stores the context in something called a key value cache, or KV cache. Think of this as a digital cheat sheet. It allows the model to instantly remember what happened on page 1 without having to reread the entire book every time it generates a new word. But there is a physical bottleneck. These KV cache vectors are massive. As the context grows, they create a severe traffic jam between the GPU's main storage, the high bandwidth memory, and its ultra-fast working memory, the SRAM. The processor ends up sitting idle, waiting for the memory to squeeze through the pipe. The AI industry is no longer limited by how smart the models are. It is actively choking on the physical memory constraints of its own hardware. The standard industry response to this problem is a technique called vector quantization. It's an established compression method designed to shrink the size of these high-dimensional data points so they fit into the cache. But traditional vector quantization has a fatal flaw. It requires offline, data-dependent training. Before you can compress anything, you have to analyze the specific dataset and build a custom mathematical codebook to translate it. That training phase takes hundreds of seconds just to index the data. When you are running a live AI that needs to generate text in milliseconds, a compression algorithm that takes several minutes to calibrate is entirely useless. Even worse, traditional methods force you to store the full precision quantization constants alongside the compressed data. That memory overhead actively defeats the purpose of compressing the data in the first place. Attempting to fix a dynamic, real-time memory crisis with a slow, static compression method leaves the model paralyzed. To solve this, researchers at Google introduced TurboQuant. It is a data-oblivious algorithm. That means it achieves massive compression instantly, requiring absolutely zero offline training, calibration, or dataset-specific tuning. Think of this as an extreme packing strategy. By optimizing the internal geometry of the data, TurboQuant fits 6 times more information into the same memory footprint without adding a single gram of physical weight. The first step of this process is called PolarQuant, and it deals directly with the chaos of high-dimensional data. Look at this Cartesian grid populated with scattered, chaotically distributed data points. This is exactly how raw AI memory vectors sit inside the hardware. To simplify this, the algorithm applies a random geometric rotation to the vectors. When you rotate a high-dimensional vector randomly, its once chaotic coordinates begin to average out. They lose their unique spikes and settle into a highly predictable beta distribution. This mathematical smoothing forces the once scattered data to align along the boundaries of a circular coordinate system. Because the data's new shape is perfectly predictable, the system doesn't need to analyze it anymore. It can instantly compress the data using a pre-computed scalar codebook. By changing the mathematical geometry of the data itself, TurboQuant entirely bypasses the real-world time penalty of hardware pre-processing. There is a hidden danger to extreme compression. Shrinking data this aggressively often creates inner product bias, mathematical rounding errors that actively destroy the AI's ability to know which words to pay attention to. To prevent this, TurboQuant triggers its second stage, the quantized Johnson-Lindenstrauss transform, or QJL. QJL acts as a 1-bit mathematical error checker. It applies exclusively to the tiny amount of residual data left over from the first stage, stripping out the bias and perfectly preserving the exact distance and relationship between the vectors. Together, this 2-stage process operates within a factor of 2.7 of Shannon's information theoretic lower bound. This reaches a level of efficiency that touches the absolute mathematical boundary of how tightly information can be packed in the physical universe. The math is flawless on paper, but the true test of any algorithm is how it behaves on modern GPU accelerators. When deployed, TurboQuant achieves a 6 times reduction in the KV cache memory footprint. At the exact same time, it delivers up to an 8 times speedup in computing the AI's attention mechanisms. This chart compares the indexing times for a 1536-dimensional vector database. Traditional product quantization takes nearly 240 seconds. TurboQuant completes that exact same task in 0.00013 seconds, while maintaining 100% retrieval accuracy across a massive 104,000 token test. Because the algorithm requires zero proprietary training, the open source community is moving fast. developers are already integrating it directly into widely used inference engines. Independent users are already running this locally on consumer-grade Apple Silicon, achieving 4.6 times memory compression without any drop in the initial processing speed. This mathematical breakthrough has officially escaped the lab, and it is actively dismantling the physical bottlenecks of both consumer and enterprise AI infrastructure. The current artificial intelligence ecosystem is built on a very specific economic reality: the necessity of buying, building, and selling massive physical data center hardware. This illustrates a shift where a software-based geometric rotation can now bypass the physical bottlenecks that once dictated how fast and how large an AI could grow. If AI models can suddenly execute the exact same workload while taking up 6 times less physical memory space, what happens to the global economy built on selling those chips? The AI industry is currently choking on a systemic physical bottleneck. Hardware prices are skyrocketing across the board as a global memory shortage, the ramp apocalypse, drains the supply chain. Then Google announced TurboQuant. The efficiency of this single algorithm immediately forced the market to ask a multi-billion-dollar question. Does this software end the memory boom or trigger an even larger supercycle? To understand the impact, look at the math. During the AI inference phase, the moment a model actually generates an answer, TurboQuant compresses the standard 16-bit cache down to 3 bits per value. That is a 6-fold reduction in memory footprint, and Google's benchmarks prove it happens with 0 loss in accuracy. Through this code alone, the physical hardware bottleneck suffocating the industry theoretically evaporates. Wall Street reacted instantly. Wells Fargo analyst Andrew Rocha issued an alert noting that TurboQuant directly attacks the cost curve for memory in AI systems. This chart shows how investors responded to that threat. Within hours of the research being published, Micron dropped 3%, Western Digital lost 4.7%, and SanDisk fell 5.7%. The panic was rooted in a specific logic. If artificial intelligence requires 6 times less physical memory to run, then the high-volume hardware procurement boom is effectively over. A weightless equation had caused billions of dollars in tangible, physical assets to devalue in an afternoon. The prevailing fear was that AI companies had hoarded mountains of expensive DRAM, and TurboQuant's optimization would leave those chips sitting unutilized in data centers. But this argument relies on a critical miscalculation. It treats the total concurrent demand for AI as a fixed, static metric. This is the Jevons paradox, an economic principle where improving resource efficiency causes its cost to plummet. When that cost drops, previously expensive applications become viable, like running powerful AI natively on smartphones or deploying complex shopping guides in retail stores. Historical patterns prove that improvements in resource efficiency never reduce total demand. They act as the catalyst that multiplies it. That is why Morgan Stanley analyst Sean Kim offered a completely opposing analysis. Kim argued that TurboQuant is a structural positive for the hardware industry, specifically because the newly freed-up memory space will not sit empty. Developers are going to take that 6 times capacity relief and immediately use it to build vastly more complex AI models, ingesting massive training data sets. TurboQuant moves the hardware barrier to accommodate a new scale of ambition. We can see this dynamic playing out right now, in the middle of a $650 billion global infrastructure build-out. TrendForce data shows that despite TurboQuant, standard DRAM contract prices will surge by 55 to 60% in early 2026. The physical requirements remain too high to ignore. Storage demand for an AI server is 8 to 10 times higher than a traditional server. There's an unavoidable hardware catch. TurboQuant delivers an 8 times speedup on high-end GPUs. Moving data at those speeds requires bandwidth standard DDR4 cannot handle. This operational bottleneck forces the industry into a faster, highly lucrative upgrade cycle toward premium high-bandwidth memory and DDR5 components. TurboQuant alters the internal configuration of an AI server, but it does nothing to shake the macro trend of exploding global AI usage. The ultimate irony of the market panic is that the technology designed to alleviate the memory shortage will be the exact catalyst that deepens it. What happens to global infrastructure when the world's most powerful AI models suddenly become 6 times cheaper to run? The AI memory supercycle is irreversible, anchored in the efficiency of extreme optimization. The future is compiling itself. Just 25 minutes after Google published a complex AI mathematical breakthrough, an independent developer used GPT 5.4 to perfectly adapt the code for Apple Silicon. The community took over immediately. But over on Wall Street, the reaction was pure panic. Major memory chip manufacturers like SK Hynix, Samsung, and Micron saw their stock prices drop by as much as 6%, almost the moment the Google paper went live. This chart illustrates the market's immediate fear. When Google announced their new TurboQuant algorithm could compress an AI's memory footprint down to 1/6 its original size, investors assumed that physical hardware demand would drop at the same rate, triggering the sell-off. That panic suggests a misunderstanding of how technology cycles actually evolve. The industry is moving away from a model of growth based on the brute force accumulation of more chips. The AI industry is no longer defined solely by physical hardware constraints. Algorithmic efficiency is now dictating the scale of what these systems can achieve. We are moving past the model of scaling massive server farms to solve every problem. Instead, researchers are rewriting the underlying mathematical frameworks to get more performance out of existing resources. TurboQuant is not a threat to hardware volume. Instead, this level of extreme efficiency serves as the trigger for an entirely new scale of global AI deployment. TurboQuant achieves these results because it approaches a strict physical boundary known as the Shannon limit. This funnel shows the Shannon limit, the mathematical ceiling of data compression. If data is pushed past that line, information shatter into noise. Because simple methods are exhausted, progress requires the vector-level encoding seen here, locking intact data together. Reaching this physical boundary signals that the era of scaling through hardware alone is over. Competitive advantages now depend on the elegance of the algorithm. Google planned for a slow corporate rollout, an academic presentation at ICLR followed by an official open-source release months later. The independent developer community moved much faster. Instead of waiting for a formal package, a single developer used GPT 5.4 to port the algorithm to the MLX framework in under 30 minutes. Infrastructure projects like VLLM and Llama.cpp mobilized instantly. They integrated the breakthrough and shared it across the ecosystem without waiting for a corporate license. This directly alters AI economics. A 70 billion parameter model previously requiring 3 high-end GPUs now operates on just 2 without losing quality. For startups, monthly compute bills can plummet from $50,000 to under $10,000. By making the logic public, builders can now deploy frontier-level capabilities on their own terms, bypassing traditional corporate release cycles. To understand where the industry goes next, we have to look at an economic principle called the Jevons paradox. This scale shows how the paradox works. When a foundational resource becomes exponentially cheaper, society does not use less of it. Instead, it finds new ways to use it in massive, unprecedented quantities. With TurboQuant, zero-loss, highly compressed models can now run natively on mobile phones and edge devices that previously lacked the memory to support them. This lower barrier to entry is expected to drive total global AI usage to levels that far exceed current projections. That once separated trillion-dollar tech giants from the rest of the industry is starting to dissolve. In this new landscape, a few lines of optimized code can offset the need for millions of dollars in server infrastructure. The hardware boom has not ended, it has evolved. The era of brute force is over, and the era of elegance has begun.